In this lesson, we'll go over the Address Resolution Protocol, or ARP. This protocol enables systems to dynamically discover the MAC, or Media Access Control, addresses of other systems that they're trying to communicate with. Every system on the network has its own IP address. For example, let's suppose that my workstation's IP address is 172.16.0.1. IP addresses are 4 bytes in length, so each of these numerals represents 1 byte of information. IP is a layer 3 address, in other words, the network layer. The system here also has a burnt-in physical MAC address, which is 6 bytes in length. Let's just make up a number here. This may not look like a number to you, but that's because MAC addresses are expressed in hexadecimal notation. That means you can have letters and numbers. Each one of these represents a byte. Those two numbers uniquely identify me from both a card perspective and a network or routing perspective. Now let's diagram a very simple network with 2 directly connected systems. Station A is here and Station B is here. Each of these systems has an IP address and a MAC address. Let's assign Station A to 0.1 and Station B to 0.2. Station A is 172.16.0.1 and Station B is 172.16.0.2. I won't write down their MAC addresses, but these would be 6-byte addresses like we saw earlier. If A is trying to send data to B, it needs to create a packet and then wrap it in a frame. Packets contain the sender's IP and the receiver's IP. So, when Station A is building the packet, it has to place both its own IP and Station B's IP into the packet header. At this point, there still isn't a physical address of any system attached to the data. That's what the frame's going to hold. Once the packet is built, ARP's purpose is to enable Station A to dynamically discover the MAC address of Station B. If Station A has never talked to Station B, it won't know the MAC address. But once a station has communicated with another node on the network, it'll remember the MAC address for future use. What ARP does is send out a broadcast frame. A broadcast frame is a piece of data intended for all recipients. It's a special MAC address built into the frame. It's made up of all binary ones. Each byte corresponds to 8 bits. 6 times 8 is 48, so there are 48 consecutive bits. That's what's going into the destination MAC address field of the frame. When the frame goes out, it'll be received by Station B and then by anyone else that may be on that network. B will pick it up and say, "Oh, you're looking for my IP address, that's me." B will recognize that an ARP request is coming in. It'll respond to A with an ARP reply. This process is called an ARP request. The ARP reply comes back as a unicast intended directly for A. Station B is telling Station A, "So you're asking for my MAC address? Well, here it is." Once A receives that ARP reply, it'll add an entry in the ARP table and store it locally. In the future, if it needs to reach the IP address of 172.16.0.2, it'll send it to this MAC address. Entries on the ARP table only stay there for a certain period of time. A Windows PC will remember it for a few minutes. Some network devices will remember it for hours. It all depends on the network device that maintains the table. The purpose of the ARP table is to allow a system to build frames that target remote MAC addresses. Whenever you need to send a packet to a system that's on the same network as you and you don't know the MAC address, ARP sends out a broadcast to request that information. And that's all for this video. In this lesson, we talked about the purpose of the ARP, which is to dynamically discover the MAC addresses of systems we want to send packets to. If you know the system's IP address, which is a layer 3 function, a packet function, then you can use ARP to discover the corresponding MAC address of that system. This is so you can encapsulate the packet within a frame and then send the frame to that system. Remember that ARP requests go out as broadcasts, and ARP replies come back as unicasts that provide the MAC address you're looking for.